Pieter Spaas is going to talk to us about stability for projection valued measures and applications to non-local games.
Well, thank you very much, Forrest, and thank you to the organizers for organizing this lovely workshop and for inviting me to speak here. So what I want to talk about today is definitely stability, so it's a good topic for this conference, and it's joint work with my collaborators Laura Baczynska, Taro Sperry, and Matthijs Vernooy. And it's going to be maybe slightly different from some of the previous talks. So really what I want to do is first talk about this half of the title. So give you one talk basically, and then you're all very lucky, you get 2 talks for the price of 1, then I'll give a talk about this. And then I'll tell you why, I'm doing both if I'm at the end. But so the first, the main problem that I want to talk about today is it's a very basic one. So say I have, given some operators A1 up through AM that are, say, approximate or even on the nose projections. I can think of just general projections and your favorite B of H, matrices, like I will eventually want to work with the 2 norms, so say some threshold and Neumann algebra. So I give you M projections or approximate projections that almost sum to 1, so such that A1 plus A2 plus AM is almost equal to 1. And I'll make this precise later on. And then the question is, then can we find actual projections, P1 up through Pm, such that the Pi is actually sum to 1, so P1 plus Pm is equal to 1, and for each I have that Pi is close to AI. Okay, so can I slightly perturb these AIs so that they actually are just a set of projections summing to 1? Okay, so that's the main problem that I'm interested in today, and I'll make precise all the approximate signs in a minute. So the first thing you may think of is, well, okay, so what does this mean, right? So it's approximately satisfying this equation. Right? So if I have projections satisfying this, I mean, there's a lot of restrictions here, right? These are just like mutually perpendicular projections adding up to 1, not much going on there.
Are they self-adjoint?
Yes, yeah. When I say projection, I mean self-adjoint projection. Yes, yeah. Thanks for pointing that out. Okay, so the first observation, well, we have talked a lot in this workshop so far about unitary representations of groups, Hilbert-Schmidt stability, right? I want to maybe turn this into something with unitaries. Okay, well, if I have M projections that add to 1, there is a very easy way to get a nice unitary out of this, right? So if I define U to be the sum of e to the 2 pi I k over n times p m times pk, sum k equals 1 to m, right? Then this is a unitary whose mth power is 1, if the pk's satisfy this, right? So this thing is a unitary, and in fact u to the m is equal to 1. So if maybe let me put that here. Okay, so if I think of something like this, even if it's just projections that almost add up to 1, you can think of it as an approximate representation of just this very easy group, right? So this here, I can view as an approximate representation of, say, the algebra or the C-star algebra or the group. Let me write it in a few different ways. So again, maybe I'll write capital P, please. So with M generators, where each of these PIs are projections, self-adjoint projections, and they add up to 1. Right? I can view it as an approximate representation of this thing. But also, right, in using exactly this is just a C-star algebra of C mod M. Okay? So, right, this is a finite group, talk is done, right? We're all happy. Okay, this is stable in every sense that you want, this is true. Okay? Okay, but so the reason that I'm not done is that eventually I will not know how many of these I have. So what I really would like is that when I do this kind of thing, I get bounds independent of M. Okay? And I'll show you in a minute the naive way to approach this. You will always get dependence on this number M. So really what I want is some kind of uniform statement over all M. And this is the non-trivial part. And so let me maybe put on this side the goal, the main goal of today, or I will also make precise everything I said over there. So what I want to say is, so given some, how do I want to formulate it? So assume A1 up through AM are positive contractions. So just positive elements of norm at most 1 in a spatial phenomenon algebra. So the trace will be important because I want to use the 2 norm. But this question is also interesting, new, and non-trivial if you just take matrix algebras. So if you want to just think about matrix algebras with the usual normalized trace, that's also perfectly fine. So such that the following holds. So assume, so I want that they almost sum to the identity in 2 norm. So if I look at 1 minus the sum of the HAs in 2 norm, this is at most epsilon. And 2, right, I want them to be approximate projections. You can do this in different ways. Let me first put the strongest possible condition and just ask that if I look at the 2 norm difference between AJ squared and AJ, this sums to also, this is also small. Okay. And what I would like to conclude is that then there exists, maybe let me give this phenomenon algebra a name, so M and trace tau. So then I want to conclude that there exist projections in M such that the sum of the projections is 1. And they're close to the AJs, so the sum of PJ minus AJ, say 2 norm squared, is less than some function of epsilon that we'll get back to. Okay, so this is the goal for today. All right. I hope this is clear. If there's questions, of course, always feel free to answer.
So in norm, is this clearly false then, the problem? Maybe you can do some rank tricks or something?
In norm,
like you could have
oh no, in norm this is this should be much easier, I think, because like I mean, so because really in the end like having positive constructions is kind of like the natural thing for the proof. We will even be just interested in it for projections. So
then you have like n-1 almost projections
mm-hmm.
and high matrices that look like 1, but then you know what I mean? Like you take a rank 1 projections, move them all a little bit
Mm-hmm.
by the same,
Yeah.
that excess gets you to the identity. But then if you want to perturb each one of them, it has to be rank 1. So you'll never fill up the whole. Get you?
Oh yeah. True. Oh yeah, because the perturbation also has to be a norm. So yeah. That's going to be very difficult. Yeah.
That's why there's these old results of Erik Christensen where he can do something like this, but he needs much more information.
Yeah, exactly. So because indeed, right? This kind of thing, right? Like, I mean, yeah, if I want projections to be close to some things in operator norm, that's usually way too much to ask for. So, yeah, I mean, all throughout, I will be heavily using the fact that I'm using the trace norm and not the operator norm, definitely.
So you said that you would like to have this for every m?
Yes, yeah. So what I would really like is that this function is independent of m. Because getting it dependent of m, as I give a sketch in a moment, this is very easy.
Capital M?
Little m, the number of projections.
No, but what about capital M, the phenomenon algebra?
Oh, just any trace of a Neumann algebra. This is actually, I mean, you can also allow yourself to find the projections in a bigger von Neumann algebra if you would want this. It's not going to change. So this is just any tracial von Neumann algebra.
If you know, universal.
Yeah. So yeah, like so the capital M is not really a big restriction if you have your AIs and you just have like an injection into some other tracial von Neumann algebras and you want to go find your projections there. That's no problem. Okay, so the first result about this kind of a problem, and that was also actually established in the setting of nonlocal games, is so maybe here's the first theorem. So this was by Paulson and Schaffhauser. I mean, okay. Maybe in their paper it's a lemma, and indeed like this naive approach is like pretty easy, but it's basically using the following very easy to prove fact in 2 lines, is that if A is a positive contraction, so let's say if I have some positive contraction A, and I look at the projection P, which is just the spectral projection of a half one of A, then P is close to A if A squared is close to A. So then the 2 norm P minus A is bounded above by, I think it was 2 root 2 A squared minus A. Okay, this is a direct calculation online. Okay, so given that we're assuming that all our AJs satisfy, that they're close to AJ, we can really just do this perturbation first, and we can kind of start assuming that the original AJs are just projections. Okay? But kind of using this fact one by one, what the proof is here is you start from your sequence of AIs. Okay, you take A1, you can do this to find P1, right? So if you start from A1, you use this fact to get P1. Okay, then you go to A2. Okay, if I cannot just perturb it randomly to a projection because I would at least want it to be perpendicular to the previous one, right? So, but what I do first is, okay, I look at 1 minus P1 times A2 times 1 minus P1. Okay, so this is still a contraction. And because the sum of the AJs was almost 1, and they're almost projections, the AIs are almost orthogonal. So it means A2 is also almost orthogonal to P1, so this will be in norm 2 norm to A2. This will be less than some epsilon prime that you can compute directly. And then you perturb this one using this fact. You get a projection that is perpendicular to the previous one, and you continue in this way. And then at the very end, you may have to correct by just like adding a projection onto something very small. Okay. But definitely 2 norm is needed here. Okay. And so you continue in this way. You basically perturb the projections, the original positive contractions AI one by one. But the error starts blowing up. So you keep multiplying by constants. And so what you get here is the goal, the statement over there, but with some function f that depends on both epsilon and m, and in fact which is exponential in m. And yeah, there's not immediately, like, if you just start working on this and you try to like do some computations, it's not immediately clear how to get rid of m at all, or even how to get this to polynomial, for instance. Okay, so, but yeah, for the applications that I will mention in the second part of the talk, we really needed to get rid of the m. Like we needed this result quantitatively, like we needed no m here. Okay. And so then our first part of inspiration came from a theorem that does kind of this, but under some different assumptions. So I'll write both the names of Thomas Wiedig and Michael de la Salle here. I think this was 22 for both of them. So Thomas Wiedig did this in the finite dimensional case, and then Michael de la Salle extended it to all tracial von Neumann algebras. So it's a similar setup, but the assumptions are, so this part is the same, but the assumptions are that, so same, but the assumptions are, one, that if I look at the sum of the AJs, I get exactly 1. So people familiar with quantum information is saying the AJs are a P over M. And 2, so this is much stronger, of course, but 2 could be a bit more relaxed. I just want that if I look at the sum, the trace of the sum of the AJ squared, this is close to 1. Okay. So the assumptions are a bit different, but then the conclusion is then the same thing holds with f of epsilon, which is 9 epsilon. Okay, so you get totally rid of the m dependence, but okay, this is weaker, but this is much stronger. Okay. You can kind of make this a less or equal than 1 and being close to 1, but this is how it's stated. Alan?
You cannot reduce the first, like the epsilon close to 1 to equal to 1 by like taking a complementary projection, like adding another one?
So yeah, so here the main problem is, and I will address this also when I write down what we actually prove, is this sum may overshoot the identity. Right, it may be close in 2 norm, but this thing could have operator norm as large as m. Right, because I'm adding m things. Like I could have very small overlap in trace, but this thing could have operator norm m. And that's kind of the issue. Again, right, like 2 norm is not submultiplicative, and like if you're not careful, like very easily the operator norm is going to start to come out and so on. So that's where you have to deal with things, and that's why this was such a useful assumption to get rid of the m here. All over this proof, do you use the fact that the norm of this sum, the operator norm of this sum, is bounded by 1? Okay. Okay, but so this is at least a result in the good direction, right? You do get rid of the m dependence. And I won't say much about the proof, but let me just in words describe. So it's actually a very neat proof. It goes in 2 steps. First, you find projections that satisfy this, but that if it's a factor whose traces add up to 1, or if it's not a factor, there are like conditional expectations onto the center. And then there's like a neat matrix trick that allows you to finish the proof, basically. But in both parts of the proof, you really crucially use this. So the first thing that one could do, which is what we first did, and if you go to the, yeah.
Sorry, another question. Can I see this condition of summing up to 1 in the Fourier picture, like in terms of a approximate representation of this? What
as
do you say
easily
about the unitaries?
Yeah, so here, yeah, maybe I should have said that more explicitly. So in all of these proofs, and also the one that we gave, we actually don't go to the unitary picture. because they're like, basically as soon as you write down this unitary for some pk's, even projections that, okay, here it would be contractions, right? So it's not even like, you don't even get a unitary. But if you take u to the power m, you just get a whole bunch of other terms. And too many, like, so that you basically automatically get some dependence on m in there unless you put much more restrictions on the interactions between these projections. And so in order to prove this, like, I mean, maybe there's something smart that someone can do that we overlooked, but it seems not the most useful way to go to the unitary picture. Yeah, because the error on the unitary is already going to blow up, basically. So if you take this proof and you kind of like try to get rid of this condition, there is a way that you can make the first half of the proof work. It's completely different, but you can make it work. But then in the second half, you do get some operator norms, and the best that we could do by trying to use this strategy is to get this from exponential to polynomial, which was still not really enough for us. But so, okay, so then in the end, like so many in so many cases, once you actually do have the proof, it's relatively simple. So it turns out you can do some relatively elementary computations. You have to just be very careful and reduce this situation, or like maybe now I will make the goal into a theorem together with my collaborators that I mentioned before. And in fact, we could do it also with the weaker assumption that just the sum of the aj squared in trace is also close to 1. And we could actually get this. Okay? And so the strategy here,
Less than 1.
Oh, epsilon. Thank you. Okay, so the idea is reduce to this case. Okay, so what we want to do is we want to take these positive contractions that we know almost add up to 1 into a norm. And we want to somehow find positive contractions that are close to them into a norm that add up to 1, or at most 1, which would be enough. Okay. So proof, right, so the idea is reduce to this thing. Right, and so the first thing that you can do is, okay, so you look at the sum of the AJs, right? And as I mentioned before, kind of, right, the sum of AJs, like, okay, in trace, the error is very small, but the operator could be like very small somewhere, but like very large in other places and so on, right? So you kind of on both sides of 1, you can have issues. And so the first thing we do is just make sure that we only have issues on one side. Because what you can easily do by preserving positivity is just add a little bit in trace to make this at least 1. Okay. So the first step is just add something. Right, so if we look at A1, for instance, we can replace it by A1 plus some A1 prime, where this is just some positive element, say the positive part of 1 minus the sum, right? Such that now the sum of the AJs is at least 1. Okay. This is very easy. And then 2, so now I want to define new positive contractions that will do the job for me so that I can actually apply this result by Wittig and LaSalle. And it turns out kind of like, I mean, the straightforward thing does end up working if you're careful enough. So if I define my BJs to be, okay, let me maybe give this a name. So this is rho. So if I let this be rho to the minus 1/2, aj rho to the -1/2. Okay, then, right, and here, right, rho is at least 1, so it's invertible, so everything is fine to do this. These bj's obviously sum to 1, so that's good, right? So then the sum of the bj's is equal to 1. So they're positive contractions adding up to 1. But then you have to be very careful in doing the computations to check that this thing is true and that they're close to the AJs. And here, right, the reason that this is tricky is exactly the fact that this rho could have large operator norm. And so, but it turns out that, you know, if you're careful, then a page or 2 or 3 maybe will give you some things. So will tell you that if you look at bj minus aj2 squared, this will be at most 4 epsilon, and the sum of the traces of the bj squared, this will be at least 1 minus 5 epsilon. Okay, so, I mean, I'm sweeping a lot of computations under the rug here, but I promise that this is possible, and once you have the right tricks, it's not too bad. Then you can apply this result, and for the people who are interested, get this with 108 times epsilon. Okay, so now, right, we have this, I guess it is in the end about, you know, very finite groups, but we have a uniform statement in M, right? Whenever you give me a family of positive contractions, no matter how many, I can kind of like perturb them all at the same time to get this stability result.
So it's important that you have sum of squares for the norm.
No, I mean, I'm kind of thinking of this as like the 2 norm squared in a sense. But yeah, I think it is false, so if you just put the norms here, I'm pretty sure.
Do you know how it evolves? I mean, is it polynomial? Is it polynomial if you put just the sum of norms?
Yeah, then it's polynomial. Yeah. Yeah, and in fact, maybe I should make a quick remark here. Michael de la Salle also points out in his paper, right? So, okay, so basically, okay, maybe you would want to put a square root here because then it's like a 2 norm, right? If you do that, then it means you have a square root of epsilon, right? So really it means that if you have here the 2 norm bounded by epsilon, then in the final estimate, you get a square root of epsilon. But there is an extremely easy example with like finite matrices that shows that is the optimal power you can do for epsilon. So most likely you can improve this 108 to something slightly smaller, but the power of epsilon you can actually not improve on. So that one is optimal. Okay. Any other questions about this? Yes?
Isn't it easier if you assume everything commutes? Like if you assume M is an abelian binomial?
Oh, then it's trivial.
Okay.
Yeah. So all the difficulty comes from that these AJs don't commute. Yeah, absolutely. Yeah, so if they all commuted to begin with, then this is very easy. Yeah. Okay, so then the second part of my talk, I want to kind of try and give you an idea of why we want this result. And in words, or the eventual goal that we had when working on this was a complexity statement for multi-prover interactive proof systems, which if those words mean something to you, then wonderful. If not, then let me give you an idea. So maybe I'm going to keep this theorem. I'm going to draw a picture here. Okay, so this is the second talk, and it will be about non-local games. Okay, so what is a non-local game? I'll give it the name G. And a non-local game, it has 4 ingredients, 3 of which we're going to care about. So I have a finite set of questions. I have a finite set of answers. I have a probability distribution on the question set, which we are not going to care about today. We'll just assume it's uniform, so I'm going to erase it. And we have a predicate v, and v is a function that goes from question pairs times answer pairs to 0 and 1. And so the interpretation here is the following. Okay, so let me draw the picture, and then hopefully this will become clear. So our game is a cooperative one. So we have a referee, and then we have 2 players that, you know, in this informatic science are usually called Alice and Bob. And when we play the game, so everyone knows these ingredients. So this is public knowledge. These are the rules of the game. So the referee will ask a question Q and Q prime to Alice and Bob, say. So they each receive a question from the question set. And then they have to respond with A and A prime. They choose what they respond, right? But something from the answer set. And this function is going to determine whether they win the game or not. If V of Q, Q prime, A prime is 1, then they win. If it's 0, then they lose. And so Alice and Bob are going to try and respond in such a way that they win the game as often as possible. Right? The way it's set up here, it's very easy if you know this function beforehand. But the whole point is that, you know, Alice and Bob cannot communicate. They're in different rooms, right? So beforehand they can discuss, they can come up with a strategy. And I'll give an example to make all this concrete in a minute. So beforehand they can discuss a strategy, then they're put in separate rooms. Each of them receives a question from the question set. They just have to, by themselves, decide on an answer, and then the referee checks whether they win or lose the round. Okay? And so the point is that Alice and Bob, they want to try to come up with a as good as possible strategy to win the game. Okay, so okay, and so let me give a concrete example, namely the games that we were interested in this work, which allows me to get to the 3rd word in the title of this long program, because I kind of have a group. I hope that's okay. I have operators, now I'm going to have graphs. So here is an example. The so-called T-independent set game, independent set game on a graph X. I'm using X because I'm already using G for my games there. Okay, so T is here just a positive integer. And okay, so the questions in this game are just T labels, so whichever set of size T that you prefer, so say 1 through T. The answers are the vertices of X. Okay, and then what is the predicate? So if I input 2 integers, 2 labels between 1 and T, and I would respond with vertices, say U and V. Okay, so this is 1. So the vertices U and V, upon getting labels I and J, win the game if and only if the following holds. And once I've written this down, I will also say what it means in words. So either I is equal to J and U is equal to V, or I is not equal to J, U is not equal to V, but also not adjacent to V. So with this I'll mean adjacency in the graph. Okay. So what does this mean? If Alice and Bob are asked the same label, they should return the same vertex. If they're asked different labels, then they should return different vertices. Okay? So if you think about it, like just classically, right? If Alice and Bob win this game perfectly, right? It should mean that this graph has an independent set of size t. That's kind of the connection, and this is actually on the nose truth, right? So what does it mean that you return non-adjacent vertices, right? If you think of like just a function that sends labels to vertices, it would satisfy these requirements exactly when the image is an independent set in the graph, right? Independent set meaning a subset of vertices where no two are connected, right? So, and so once you see that, right, so it's basically trivial to conclude that if this game is played on a graph that has an independent set of size t or more, then Alice and Bob can always win this game by just agreeing beforehand on an independent set and the labeling, and then just answering according to that labeling, right? So like, I don't know, let's, like if you have like a very trivial example, like, I don't know, maybe something like this, and say t is equal to 2, I mean, this will of course be very easy, right? And for instance, right, there's at least 2 vertices in here that are not connected. So for instance, Alice and Bob could agree to label this one by 1, this one by 2. Oops, maybe not too many circles. And just when asked label 1, they return this vertex. When asked label 2, they return this vertex. And then they will always satisfy this. Okay. And in fact, you can show that if Alice and Bob respond to a so-called classical strategy where each of them just has a function from labels to vertices, then they can win this game always if and only if the graph has an independent set of size t. Okay. And so really, the way that I think we should think about this game is in this game, Alice and Bob are trying to convince the referee that there is an independent set of size t in the graph, even when there potentially isn't, but we're trying to convince the referee that this is the case. Okay. Does that make sense? All right, so now why is this an interesting question to ask? So basically, classically, like what I just said, it's just asking whether this game has a perfect strategy. It's just the same as asking whether the graph has an independent set of size t. So it's just a reformulation. But people in physics and computer science and mathematics came along and were like, well, Alice and Bob, they may not be able to communicate, but maybe they can take advantage of quantum mechanics. Okay? I don't know what that means. Right, so somehow it means that they have some entangled state that they share and that they can perform measurements on. They cannot communicate through this state, but they can have correlation, basically. Okay. I won't say much more about it, but let me give you the mathematical picture of that. Okay. So here is a quantum strategy for this game. So quantum strategies for G. So a quantum strategy consists of the following. I have Hilbert spaces for both Alice and Bob. For instance, they could be finite dimensional, that's already very much non-trivial. And then, and here you will see why there is going to be a link with the theorem from before. Essentially, so I will, okay, maybe I'll first write, I have some element of the tensor product of these Hilbert spaces. This is my entangled state, right? And so basically, this psi, okay, it's lives here in the tensor product. If it was just a vector tensor another vector, then you could do nothing really, but it could be like not a simple tensor, right? And that's the whole point. And then Alice can basically like act on the A part, and B can and Bob can act on the B part, so they can do measurements there. And the measurements are exactly projections that add to 1, basically. So what I also have is, for every possible question in the game, I have sets of projections, P, Q, A, where A ranges over A, on HA. So these are Alice's operators, and then also I have some operators for Bob. So let's say maybe P tilde QA, A and A for Bob. To the best of my understanding from people who explained this to me from quantum mechanics, if you would assume that Alice, say, has an observable, something that she can measure on HA, say for simplicity, it's a finite dimensional unitary matrix, right? So it's a finite dimensional unitary that you can act with. Then the possible measurements are its eigenvalues. Okay? And this would just be the projections onto the eigenspaces. And their traces somehow correspond with the probability that you get each of the measurements. Okay. And so when you have these ingredients, assuming that something quantum mechanical is happening and Alice and Bob are using these operators to actually measure and then respond. So here, the probability of Alice and Bob answering the pair A and A prime upon receiving Q and Q prime as their respective questions is, and usually it's denoted by this like probability of A prime given Q prime. It is the inner product of P Q A tensor P tilde A prime Q prime acting on psi. Okay, so these basically, right, and we can all forget about quantum mechanics now. The probabilities of answering certain pairs of answers on certain pairs of questions is completely governed by these projections. Oh, I forgot to write here, such that the sum over all A of PQA is 1. And same here, such that the sum over A prime of P tilde Q A prime is 1. Very important. Okay, so these are quantum strategies. Okay. And if we just accept that for now, right, then really figuring out whether we have good quantum strategies is playing around with these projections. Right?
So why in this intuitive picture you need to vary the number of projections?
Here I don't have to yet. So here for a fixed game, we don't. We know the number, because the number of projections in each set is just the same as the number of answers. But later I'm going to have families of games with increasing answer sets, and then I will need this. Yeah, but for a single game, you don't, absolutely. Okay, and so, right, so once you believe this last line, right, when I give you a strategy, meaning I give you these Hilbert spaces, this vector, and these projections, you can compute what the winning probability is for this game, right? So the winning probability is, okay, let me call this strategy S. So the winning probability, which is denoted by this omega star GS, so the quantum value as it is denoted for the game G using strategy S. And you can just write down what it is, right? It's the sum over Q prime, A prime. I guess I kind of, right, remember there was this like kind of probability distribution we didn't care about, but like the probability of being asked a pair QQ prime is just 1 over n squared, say, if it's uniform, times the probability of answering a prime given that specific pair. And then we're wondering whether we actually won, so times v of QQ prime AA prime. Okay, and so, right, in general, one likes to know when you can have perfect quantum strategies, for instance, when this is equal to 1, or maybe when this is close to 1. Right, so then the quantum value of G is just the supremum. So the supremum over all possible strategies that you could write down of omega star GS. Okay. And for instance, a common question is this equal to 1 or not? All right, so let me maybe write down the 2 main results that we were after, and then we used the stability theorem that I mentioned. And then hopefully I have a bit of time to show like why this was important. Okay. So there's a first theorem that we showed. So what we were interested in, maybe first in words, is, okay, these t-independent set games, they're very concrete, they're very nice, you can kind of understand them. But in general, there is a lot of just like non-local games. There's a very wild family of them that you don't necessarily understand. And one of the implications of MIP star equals RE, for instance, which was mentioned earlier, is that this class of non-local games is very wild. And in general, you can, this number is not computable in the class of non-local games. But of course, I mean, no. There's a lot of Q's and A's and functions that you can put here, and it's very hard to deal with them, to work with them. And so one of our goals was to get a similar kind of complexity result for this much nicer family of games. And so in order to do that, what we wanted to do is reduce the class of all non-local games to this nice class of independent set games. And that's what this first theorem is doing. So let G be any, okay, we're really working with synchronous games, which is also what MIP star equals RE deals with. I'll see if I have time to talk about it, but for us, it's not a very restrictive condition. It's a non-local game. And denote by T the number of questions in it. Okay. So then we show, let me check the number. So then we show that there exists some graph X G, the graph, such that the T independent set game, which I'll just denote by XGT, satisfies the following. So there is two parts. The first one is usually called completeness, which says that if the original game G that you started with has value 1, so it has almost perfect strategies, then also this graph game that you get out of it has quantum value 1. And soundness, and this is the tricky part, which is saying that if the quantum value of the original game was bounded away from 1, then the quantum value of the new game, the independent set game, is also bounded away from 1. Epsilon 8 over t to the 4.
So it's also undecidable?
Sorry?
So it's also undecidable for these.
Yes, that will be the corollary. And here kappa is just some universal constant.
And this transformation is like a polynomial construction?
Yeah. So you have to make sure that this is like
Polynomial
proper,
transformation.
like computable and so on. There's Turing machines in there and so on. But like, yeah, it's very concrete.
Is it even clear for which t, like you get a separation between classical and quantum strategies? Like for t equals 3? Or?
I'm not sure. I don't think it should be too big, and you can probably write down some examples, but I'm not sure if anyone has to try to find like the minimal possible t. Yeah. So maybe let me go here and I'll keep it high enough. So the corollary here is, so what we now want to do, so okay, if you don't, right, there was a little bit of discussion earlier, if you are still a bit unsure about assuming MIP star equals RE, you can say if MIP star equals RE, then this corollary, otherwise it's just true. But so if you just take here the class of all synchronous non-local games, you still don't get complexity because you have this T here, right? If you look at all possible non-local games, right, this T is going to increase in size and this gap is going to close and you have a problem. Okay? But there was a follow-up paper that could actually get similar results for games with fixed question size. Right? But that's why the answer size is going up and why we need that result. And so the corollary that we could get out of it is still with some work, but so there exists some constant strictly between 0 and 1, and some fixed t in n, such that and I'll say in a minute what this is, the 1s gapped promise problem I've forgotten family. And a family of T independent set games such that this 1s gap promise problem for it is undecidable. Okay. And so what is this gap promise problem? It's I give you a game from this family. I promise you either the quantum value is 1 or it's less than 1 minus s. And you have to tell me which one of the two it is. Okay. So this should be easier than deciding whether the value is 1 or not, right? But even this easier problem is undecidable for a class of graphs, really, on which you play the T-independent set game for a fixed T. Okay.
You deduce it from the MIP Kochav equal RE, or you can prove the MIP Kochav equal
No, we use it. We use it. Yeah. So for this, we need to use it. This is completely its own thing.
If you would know this theorem, you could.
If you would know this theorem, then definitely you would. Yeah, this is stronger. This is stronger than MIP star equals RE. Yes. And one of the reasons that okay, I mean, it's nice that this is a much more concrete class of games, but also it gives a very sharp distinction between the classical and the quantum case, because this problem is completely trivial if you only use classical strategies. Meaning it's actually trivial to decide whether these graphs have independent sets of size t or not. This is decidable in polynomial time. Because if you have t is fixed, so you just list all the possible subsets of size t of your graph, which is polynomial in the size of the graph, and you check all of them. Okay. The thing is, the quantum value can be 1 without there being an independent set of size t, and deciding the quantum value in this case becomes much more tricky. And so this was actually the first example now. So we already know examples where quantum and classical behave differently, but this was the first example where the classical problem is very easy, even to decide what just one or not, but the gapped problem becomes hard in the quantum case. And yeah, I have only, maybe let me say one thing, so to actually like a bit more strongly connect the theorem over there to here. So I can draw you a picture of the graph that we get. Okay. So for the graph xg, let me maybe do it here. And then I'll say in words. So what we have, so the vertices is questions times answers. And a pair QA is adjacent to a pair Q prime A prime if and only if V of Q prime A prime is 0. If it's not symmetric, you also have to ask the other one, but I'll skip that. So basically the edges are telling you on which pairs of questions and answers you lose the game. Okay? And because these games are synchronous, the graph is kind of going to look like this. So you have like a Q with maybe A1, and then that same Q with A2, and that same Q with A3, and so on. And here you have like all the points that are Q, comma, some answer. Without defining it explicitly, the synchronicity is going to tell you that these are all connected to each other. So this is just like some complete subgraph. And then here you have maybe Q1 and also everything with Q1, and then here you have Q2, and then everything connected to that. And so the graph is going to be some complete graphs with some edges in between them that are going to depend on what this function is exactly. Okay. So immediately you can already see classically independent set of size T is the maximum you can have, because you have T of these complete components. Okay. But so to go between the two here, so this one is easy, so I will do some work, but this one is relatively easy. So for this one, the way that you prove this kind of thing is by the contrapositive. What is the contrapositive? Is saying if the quantum value is close to 1, then the quantum value here is close to 1. Okay. And what you can then do is, from the quantum value being close to 1 here, you get a quantum strategy that performs very well. This quantum strategy gives you an operator for each of these points in my graph, right? And so to get the quantum strategy for the original game, so here, right, you see, I have, right, because T here was also Q, so I have like Q many questions, and Q times A many answers. Here I only have Q questions and A answers, so I have too many operators, okay? And so what you will have to do in order to go from a strategy here to a strategy here is combine projections. So you have to like sum many of these operators to get one projection for the strategy here, and you need those to be actual projections that add up to 1 in the end. But because the strategy that you started with, right, contrapositive, was only close to 1, all of that is only going to be approximately satisfied. And to get this kind of corollary, and to get here something that is independent of the number of questions, independent of the number of answers in the original game, you need a stability theorem that is independent of the number of things you're adding, because the number of things you're adding involves the number of answers, because of this. So that's how they are connected. Yeah, so I hope that convinced you that these two are connected, and yeah, thanks a lot for listening.
All right, any questions?
Yeah,
Can these strategies give something for multi-party computation, multi-party quantum computation?
Yes, yeah. So these non-local games are very much related to like quantum computation, and here I'm focusing on just 2 players, but you can have more as well. And Yeah, like so you can encode many things about multi-party communication in these non-local games.
The one where Alice in Dawn does not learn anything except for saying.
Exactly, yeah, that's the whole point of this separation, and like there's various other conditions and restrictions that you can put on there, on like how much like correlation they can have and so on, so yes, definitely.
So I'm trying to understand the main theorem, and it seems to me like there are two things. One is that the reduction that every local game, it seems like as far as computationally you can imagine that every non-local game is an independence game.
Yeah, that's really this.
And second, you say that it's actually a gapped game. So is this like two different
yeah, so
or also in the original thing, it's a gapped. The original thing about non-local games, it's a gapped question.
So this is really the kind of the gapped version. You could also ask this without epsilons and just say, if this is strictly less than 1, does it imply that this is strictly less than 1?
Right.
That is what is usually called a reduction.
Yeah.
When you have like an epsilon here, and then like, again, a uniformly bounded epsilon here is called a gapped reduction or a gap preserving reduction. And that is what allows you to get that S over there.
So what does MIP already say about the games? What is undecidable?
That it's
the gapped
games
is undecidable, and what you do is you say might as well always assume that your games are independence games.
Exactly. Yeah. So MIP star says something about the gapped promise problem, like I explained over there, for general synchronous games. That is basically undecidable. And then through this reduction, like you say, right, this really tells you, like, if you have a non-local game, you can just map it to this associated t-independent set game and kind of preserve.
And were there reductions before of this form that says that any game you can think of it in some sense as a much more simpler object, like just?
There were some reductions, but most of them were not gap preserving. So there are several known results where you have just like strictly less than 1 and strictly less than 1, but getting this gap is usually the highly non-trivial part, and this is why we needed that.
There's the result of Alex, Michael Chapman, and Louis Bowen, where they do a reduction to tailored non-local.
Yeah. So
That's also a gap reduction.
Yes. They in fact also copy a large part of the original proof of MIS.
Yeah, but that's a separate thing.
Yeah.
All right.
Sorry if I was mentioned, can you say something about that T? Do you have some estimation on how?
No. So yeah, basically both the S and the T, we don't really know what they are. The T is going to be very large and the S is going to be very close to 1. In with what we can do now, but like, because it relies on several other results where like, at least we could not, like, it looks like you get like some exploding like because the T comes kind of from like some big parallel repetition kind of thing, and like it's going to be very large. But as far as we could see from the papers that we rely on, we get this result, but we don't really get estimates on T or S. Yeah, that would be a nice thing to know.
Okay. 2 more.
I already asked.
Yeah. One more.
So the question about this theorem, if I know that it is a group phenomenon algebra, what it tells me about it tells me something about the group?
But the M?
Yeah.
No, I don't think that's going to help you.
There are what's called linear system games, which are associated with groups, and this being undecidable for them is like the group being not.
But then, yeah, these projections here, just living in the group, I don't think it would help you much, no.
All right, let's thank Pieter again.